We're going to review some of the basics of large language models. I think we have like mixed levels of experience here. So this is, if you have never heard of a large language model before or used one, this is going to be horribly insufficient introduction to what these things are. If you've been using them every day, you're probably going to be, it's going to be a little bit repetitive, but it's important to know like at least a little bit of how these things work. Then we're going to cover kind of one of the core skills of building language model applications, which is prompt engineering. Right now, one of the trickiest parts of getting these applications right. And so we'll cover some like kind of tips and techniques to make this work well. And then as we get towards the afternoon, we'll talk about augmenting language models, which is how you take all the information that you need the language model to have and inject it into the model so it can solve the task that you actually need it to solve. So that's one of the biggest subjects, and we'll cover it for the most time. Then in the afternoon, we'll talk about kind of like how do we systematize this? So once we have the pieces in place, how do we actually go from a system that kind of works as demo and make it into something that works well in production? So we'll talk about a philosophy for building language model applications kind of that's analogous to test-driven development. And we'll talk about kind of some of the operational aspects of building language model applications as well. And then in the afternoon, we will kind of like do a walkthrough of a code base, like an example code base of a kind of like a language model application that's actually running in the Discord channel that there's a link to here. So we have a Discord for FSDL that has like, most of the folks who have ever taken a class with us, there's often like pretty interesting discussions going on there. So feel free to jump in the Discord here. It's a good way to stay in touch with folks after and also interact with our fun Ask FSDL chatbot as well. And so we're going to cover today like two very different ways of building this chatbot. The first is like the simple, easy way that doesn't work very well, which is to use the like brand new features of the Assistance API that OpenAI released last week. And then we'll cover a kind of more complicated, more in-depth process of building this application, the old school way as of 2 weeks ago, which works quite a bit better today. So you'll see like sort of two different ways of building an application like this. So let's dive in. All right. First of all, just a little bit about FSDL. We really try to sit at the intersection between like what you'd think of as a traditional machine learning course that focuses on fundamentals and techniques and algorithms and things like that, as well as covering a lot of more practical aspects of building applications. And so with a focus on like actually shipping things and not just writing papers. And we also try to mix in a good amount of state of the art. So it was one of the reasons why we typically do these classes like once or twice a year is because we're always updating them with latest materials. And so hopefully we'll cover some stuff that you haven't seen before. Just a quick introduction. So I want you to start by imagining a world, okay? In this world, there's disturbingly simple computer programs that can mimic human cognitive processes. Humans are starting to form emotional attachments to these chatbots. Computers can play chess, they can write mathematical proofs, they can pass difficult exams, and you can actually even get intelligent investment advice from AI, right? So what is the world we're talking about here? Is it the future? Is it the present? Is this like what LLMs have enabled? Actually, no. This is all from the past. This all happened in 1965. So ever since kind of the dawn of artificial intelligence, people have been making claims about the capabilities of these systems. And we've seen isolated individual examples of human level or past human level capabilities from computer programs. So you might ask, what's different this time, right? Why do we feel like this is an exciting time to talk about AI and it's not just 1965 all over again? And I think the key difference is that now, rather than having a bunch of handcrafted individual computer programs that can each do one task really well, we're starting to have a single tool that can do a lot of really powerful human level or even past human level things, which is this tool called a large language model. So what is a large language model? Large language models, as the name suggests, they model language. So what does that mean? If you imagine a paragraph and you imagine writing a single word of that paragraph at a time, if you learned how to guess what the next word was going to be, if you learned how to predict what the person was going to write in the paragraph, you'd get pretty smart. And that would be especially true if the person wasn't just writing text, but they were also writing all kind of like logic, math, chemical formulas. If you could always predict what was going to happen next, you'd have a lot of knowledge about how the world works. And so it turns out that large language models are really good at this. And they can predict a lot of things very well. On top of that, large language models unlock kind of what I think of as like a new paradigm for computing, which is language user interfaces, right? So in contrast to graphic user interfaces from the current or previous era of computing. Language user interfaces, this is not a new concept. It has its, a Wikipedia page, and people have been talking about this since the 1960s. I'm in a little bit of trouble with slide, here we go. But what's really powerful about LLMs is that they've unlocked new ways for us to interact with computers by just typing, asking what we want from them, rather than needing to have a human design what is possible to interact with. So language modeling, according to a lot of folks who are deep in the AI world, folks often consider language modeling AI complete. What that means is if you were able to model language perfectly, if you were able to predict the next word in the sentence as well as you possibly could, then you would have a system that is, you could consider artificial general intelligence. So what does AI complete mean? Concretely, it's a pretty slippery term. It's not something that's very precisely defined. But the core idea is that language modeling is really hard, and if you could predict the next word in all kinds of different things like chemistry and math and science and history, then you would have to have a very condensed model of the world in order to predict what's going to happen in the future. And that condensed model in the world is in some sense, some form of intelligence. So before we get into how to actually leverage these tools and what you can build with them, I want to talk a little bit about what happened last time. So what happened the last time people got really excited about AI in the 1960s and after that. And so the history of AI is kind of a history of overselling and under-delivering. So each of the past 2 or 3 times that folks have started to feel the way that they have felt now, which is hey, this technology is amazing, the world is going to be so different in 5 years, the hype has outpaced the actual impact. And that's led to several AI winters, where people sort of felt the hangover of this overpromise, and it led to AI falling out of fashion for long periods of time. And so why was that, right? I think one of the core reasons is because the high expectations were coupled with amazing demos, but they were never actually matched by the product experiences that people were able to create with them. So the high hopes were never actually realized for most people. Most people never interacted with an AI system of this previous generation that could do anything useful for them, right? So people eventually get disillusioned with the overpromising. Kind of a little bit like what happened with crypto a few years ago. And so, and there's numerous examples of people sort of complaining about this over the years. So I think the key point here is, in order to prevent this from happening again, it's not just about how amazing a demo OpenAI can produce, or how many papers are getting published, or what people say this is going to be able to do in 5 years or 10 years. In order for this technology to do anything, we need to actually build products that create value for people. And the good news is, this time around, there's a lot more happening than just research. There's all kinds of products that are being developed. ChatGPT itself is one of the fastest growing products of all time. So there's hope that this time it's actually real. And finally, there's tinkering, right? So people are actually, the most encouraging part of all of this has been, if you spend time on Twitter or around the Bay Area going to LLM meetups, there's thousands and thousands, maybe even tens or hundreds of thousands of people that are just tinkering with this technology, trying to build useful things with it, which feels really different than when I got into the field back in 2015. So that's the good news. There's a lot of people that are trying to build products with this technology, and there's a lot of tinkering happening. The bad news is that in AI, this has always been true, and it's still just as true as ever. The gap from having an amazing demo, a thing that you can create these days in 15 minutes that shows the promise of what you're trying to build, the gap from that to having an actual working product is huge. So self-driving cars are a classic example of this. You might remember back in 2016, 2017, there was a ton of hype around self-driving cars. The demos looked like these things were basically ready to go out into the world. People thought that we were, a handful of years away from never having to drive again. Now in 2023, 6 years later, we're just starting to see kind of the earliest phases of this technology actually coming to fruition. So a long, hard six years, hundreds of millions, billions of dollars spent to go from what looked like it was already working to something that is just barely starting to work. And so that gap is actually maybe bigger than you remember, because while people were, the last time people got really excited about self-driving cars was, 5, 6, 7 years ago. The first time that people got really excited about self-driving cars was actually in 1988, when researchers demonstrated that you could have a vehicle drive itself on highways all the way back then, right? So I think like the hope would be that we're in the 2017 era of large language models, or potentially even past that. And then the fear is actually maybe we're still in the 1980s. And so let's hope that we're not there. But again, I think the thing that would point you to believe that we're further along is that there are a handful of breakout products powered by this technology. So ChatGPT being probably the most prominent, but GitHub Copilot being another like really powerful example for those of you who've tried it. And then another kind of like favorite of ours at FSDL is Descript, which is a video editing tool that's powered by LLMs to make video editing way easier. So there's not, I think maybe when we first taught this course, this version of the course back in April, I was hoping by now there would be dozens, hundreds of LLM-powered applications that people were using every day. There are not yet, but there are a handful, and so that's really promising. So what we're going to cover today is like how to build these like great LLM-powered products. If you want to try to help avoid the AI winter, build an amazing product that couldn't have existed like maybe even a year ago, it's a lot more difficult than just building the first demo. And so we'll talk about some of the ways that you can kind of get from that first demo to a real working product in production. But before we get into any of that, we're going to talk a little bit about just kind of some of the basics of large language models. Like, what is this technology that we're working with? First of all, one thing you might be asking is like, why do I even need to know this? Like, isn't an LLM just an API that I can call, like any other API that I've called in the past? And I would say like 80% of the time, you can more or less treat it that way. Most of the time when you're working with LLMs, it's a pretty good mental model is it's just a black box that can, you'll develop intuition for as you interact with, but it can, take in some text as an input and generate some text in a response. But the other 20% of the time, when that intuition starts to fail you, it can be really valuable to know, at least at a high level, what's happening under the hood for these systems. And so what does that give you? It can give you, sometimes as you build with LLMs, you're going to start to hit their limits. Even though the limits are really high, you'll hit them very quickly. And so if you understand the way the models work, you'll start to build more intuition for when they might fail and why they fail when they fail. It can also help you find bugs. There's still, the technology is getting closer and closer to something that you can just plug and play out of the box, but there's still kind of like subtle bugs that you'll encounter as you use these things, like tokenization. And some of the kind of like core intuitions about machine learning are still really valuable to know. So LLMs, like most of the time when we interact with them, it doesn't feel like what it felt like to do machine learning 5 or 10 years ago. But under the hood, LLMs are still machine learning. And so some of the like kind of core principles of machine learning, like overfitting and underfitting, which we'll talk about in a second, still apply, just in more subtle ways. So let's first talk about machine learning at a high level. In traditional programming, what happens is a developer builds a program, and that program takes an input and it produces output, mostly in a deterministic way. In machine learning, the role of the programmer is different. So rather than producing the rules of the program itself, instead the role of the programmer is to produce training data. Training data gives the algorithm examples of the behavior that it's supposed to have. And then once the model has been trained, then it's able to look at new novel inputs that follow a similar pattern to the ones it was trained on and look at those and produce outputs. So if you've spent any time in machine learning, you'll be familiar with many different types of machine learning that people use. Kind of at the highest level, there's basically 3 kinds. So there's unsupervised learning. In unsupervised learning, what you're trying to do is you're trying to learn the general structure of some data. And the reason why you learn the general structure of some data is because you want to be able to produce similar data to what the model was trained on. And so that's kind of that's the closest to what language models are doing today. Second type of machine learning, and probably the most widely used one in practice, is supervised learning. In supervised learning, what you're doing is, rather than learning the structure of the data, you're learning a relationship between two different types of data, between an input data, like an image, and then a label, like a description of what's in the image, or a translation or a transcription of some audio. And then finally, there's reinforcement learning. Reinforcement learning is probably the most different type of machine learning from the others. And in reinforcement learning, rather than kind of operating on some data that you're given, you're instead learning to interact in an environment in the world. And so reinforcement learning has been applied to, like mostly these days, video games. But it's also relevant in the language model world, which we'll talk about a little bit later. So these days, that's historically, like if you look at machine learning, you'll see those three types. These days, there's mostly just two that are used in practice. There's supervised learning, where you are taking some input and you're mapping it to some deterministic output. And then there's self-supervised learning, where you're doing something similar. You're taking an input and you're mapping it to an output. But in this case, that output is what happens next in the sentence or in the game that the AI agent is playing. So how does this work? There's a lot of different algorithms that you can use for machine learning, dating back decades and decades. You've probably heard of a lot of these. Logistic regression is a simple type of machine learning algorithm. Support vector machines were a really popular type for a long time. Decision trees, still widely used in practice for a lot of applications. But one is becoming dominant, and that's neural networks, which is also called deep learning. So what are neural networks? Neural networks are a machine learning algorithm that's inspired by the human brain. And the way that the brain works, if any of you are neuroscientists or biologists, I'm sure I'll completely butcher this, but at the highest level, the brain is composed of billions of neurons. What the neurons do is they receive electrical inputs on one side, and then they transform that into electrical outputs, which are passed to other neurons in the brain. And ultimately, by composing many, many neurons, you're able to produce very complicated types of behaviors. And so you can also think of the brain itself as having like high-level inputs and outputs that are transformed through the process of like billions of neurons interacting with each other. So for example, the high-level input is you might see a cat kind of running across the floor in front of you. And the output that might produce is you might say, there's a cat. And so there's a really complicated process happening in between those two steps, but the inputs and outputs are very simple. So how do we formalize this in machine learning? In machine learning, we also have a concept that's called neurons. But the neuron is like a highly simplified mathematical model for what's actually happening in the brain. So rather than transforming electrical impulses, instead the neuron in a neural network basically does some like really simple linear algebra to transform the inputs into an output. And so the inputs in a neural network are basically like a vector of numbers. So this simple input that you might want to put into the model needs to be transformed into a vector of numbers. And then at each step in the neural network, you do a matrix multiplication, where you take that vector of numbers and you transform it into another vector of numbers. And as you do that more and more times with some other functions applied in between, you are able to produce really, really complicated transformations. How complicated are these transformations? Well, it turns out that neural networks, like with some assumptions, the main one being you need to have one other thing called a nonlinearity happening in addition to just the matrix multiplication, you're able to actually model any function. So neural networks can model any function that you would want to model. So this is a very general class of algorithms. And so, the mental model that you should have when you think about what an LLM is doing is it's taking a vectorized representation of the sentence. So it's a transformation of the sentence into just like a long list of numbers. And then it's doing a bunch of linear algebra. It's like multiplying that vector by a matrix, and then it's multiplying the resulting vector by another matrix. And by doing that many, many, many times, it's able to transform that input in arbitrary ways. So that's kind of like the high level intuition for what a neural network is. So I think the relevant question is like, okay, if a neural network can represent any function, if it can do anything, then how do I get it to do the thing that I want it to do? How do I get it to have the behavior that is important for me? And the process that we have to do that is training. So in training, you take some data. That data usually consists of a set of inputs and a set of labels. In computer vision, those inputs might be images, and the labels might be, a description of what's in the image, like a cat. In language models, the input is the sentence, and then the output is the next letter or the next word or the next token in the sentence. Then we take this like potentially massive set of data that we have, and in language modeling, the data is in fact massive, and we sample just a tiny little batch of that data. So we might have billions and billions and billions of sentences that we're training the model on, but at any given point in the training, we're going to sample just 10 or 50 or 100 of them. We use the current version of the model, even if that model is totally untrained, and we make a prediction. So we say, okay, what do I currently think the next output is? Once we have that prediction, we're able to use that to compute a loss function. So the loss function is a mathematical way of formalizing like how close was our guess. So we predicted that this is an image of a dog. In fact, it's an image of a cat. That's an error that we can then use to improve the model. Once we have that error, once we have that loss, we use a process called backpropagation to take that loss and use that to adjust each of the matrices in the neural network. So that loss, the difference in what the target value was, like what is the actual answer here, and the answer that the model currently is predicting is backpropagated through each of the matrices in the neural network by basically using really simple calculus. And that produces an adjustment to each of those matrices. So what's happening is the model over time gets incrementally better and better at guessing what that output is because we're essentially doing like some really simple calculus to determine how the matrices should be updated to make the model's guess closer to the true output. And you do this over and over and over again, and the average loss, like the average difference between the predictions and the outputs, goes down over time until eventually you have something that looks a lot like the output that you want to have. So like sometimes I reflect a little bit on like how wild it is that just doing this really, really simple process of having random predictions and then doing a little bit of calculus to try to make the predictions closer to the true outputs produces something that feels as intelligent as language models. So pretty amazing phenomenon. So another part of how neural networks are trained that's I think relevant to understanding language models is in machine learning in general, you don't train on all the data that you have available. You instead split your data into a subset that's used for training and then two other subsets that are used for validating the trained model in different ways. The reason this is important is because models are really powerful and language models have tons and tons of weights or parameters in them. Really big matrices, you can think of it as. And so the effect that has is that models are very good at memorizing the data that they're fed when they're trained. And so really common phenomenon in machine learning is you train your model, it looks like it's perfect, and then you try to make it generalized. You try to make it work on any other data other than the ones that were in your training set, and it performs so much worse than what you thought it was going to perform based on training. And the reason is because the model is memorizing the specific examples in the training set rather than learning how to generalize to other similar examples. So to avoid this, we have data that we know the answer, but we are not actually training the model on. And we use that for validating whether the model is doing what it's supposed to be doing on novel data points, as opposed to the data points that we fed it in for training. So this is the reason why I think this is like one of the conceptual parts of machine learning that's important to understand for LLMs is because this same phenomenon applies to experimentation with your prompts. So if you've spent time doing prompt engineering, then you've probably had this example where you have a few types of inputs in mind, like a few documents that you want to summarize, and you work on your prompt and you improve that prompt, and then it's doing better on those 3 documents that you tried it on, and then you try it on like a 4th document and you realize it's actually doing much worse. So this is a similar phenomenon where anything that you use to tune the model, anything that you use to try to like improve the outputs of the model, it's like the result that you measure on those things, you should make sure that it works on other things as well, because ultimately the goal of these systems is to generalize, not just to work on a handful of examples. One challenge of training models is that it's really slow. And this is particularly true with like modern deep learning models, where oftentimes these are trained on millions, hundreds of millions or even billions of inputs. And so pre-training the model is like kind of the core training process, where you start from nothing, a model that doesn't understand how to do your task even a little bit, and you end up with a model that solves that task pretty well on this massive amount of data. And so pre-trained models are things like GPT-3, GPT-4, or any of the open source models that you might have interacted with. But one of the nice things about deep learning is that once you have a model that's been trained on this massive amount of data, you are able to just keep going with the training process on a much smaller amount of data, which is maybe the data that is relevant to your task, rather than the one that was relevant to the task of the people who trained the original model. And since you're training on much less data, this process is much faster, and you can get pretty good results quickly. And so, these days, for most of you, you may never actually train a model from scratch at all. You may actually almost always start with a model that someone else trained, and then just adapt that model through the exact same process to work for the task that you're trying to solve. And one of the great things about working in deep learning in 2023 is that there's tons of these pre-trained models available. So you can go on Hugging Face and you can find thousands and thousands of models that someone else has trained that you can that may not work out of the box perfectly for your task, but you can take those models as a starting point, and you can use a lot less data to make them work for the tasks that you're trying to solve. So Hugging Face is kind of the best place to go look for pre-trained models if you're trying to find a good starting point for your task. But yeah, 180,000 of them. It's crazy. And this is actually, I think this number is out of date. It's probably well over 200,000 now. One of the other great things about working in deep learning in 2023 is that before around 2020, pretty much any task that you could think of had its own like bespoke neural network architecture. And if you went to a conference like NeurIPS, a lot of the, which is kind of the main conference for deep learning these days, a lot of the focus of the research community was just making incremental changes to model architecture, which means like changing the ways that the matrix multiplications are arranged in order to incrementally improve performance on specific tasks. And so computer vision, natural language processing, speech, translation, these all had their own bespoke model architectures that people put a lot of effort into creating. And so if you're trying to get up to speed in any new part of the field, there's a lot to learn. But now, pretty much all of the field is converging on a single neural network architecture called the transformer. And so this is really powerful because it means that a lot of the tooling, the infrastructure, and the knowledge is starting to consolidate. And so you don't have to learn as much in order to start building a good model for your task. So this all started with a paper called Attention is All You Need. And this was kind of like very groundbreaking at the time. And a lot of people, when this paper came out, kind of saw that this was likely to become a sort of a dominating force in the field. But it's difficult to underestimate like how much impact it's had in 6 years. So I'm not going to review like the details of this architecture, but what I will talk a little bit about is like why is the transformer become dominant? So the transformer is becoming dominant because it's very general purpose, right? So it can represent any function. You can easily optimize it to solve whatever task you're trying to solve. But both of those things are true for deep learning in general. The amazing thing about the transformer is that it's highly efficient to train, which means it's super parallelizable, which makes it like very, very well suited to training on large numbers of GPUs. which is, like allows people to devote like tons and tons of computing power to training these models. And spend, in some cases, like tens or hundreds of millions of dollars to train a single model, which was, with previous architectures, was just never really possible because it didn't scale well enough for that to make any sort of sense at all. Unfortunately, we still mostly don't really understand why transformers work, though. So there's a lot of work that people are doing in the research community around what's like often called interpretability. Yeah, here we go. And so a lot of this work is coming out of a group of researchers at Anthropic. And if you want to like try to build a deeper intuition about why transformers work or what's going on under the hood, I'd recommend checking out some of their papers. But unfortunately, like I think this is at best a highly, highly incomplete picture of what's actually happening inside of a transformer. And I think it's fair to say that like most researchers feel like we don't actually know what's happening inside of these models, which can create a lot of problems, but is the reality of the technology, and it's probably not going to get any easier. Okay, so I intentionally didn't talk about the transformer architecture just for the sake of time. But you might be asking, like, is it actually worth spending the time to understand the way this architecture works, or maybe even to code it up yourself? So I would say it's like really not necessary. You can, if you have a high level intuition of machine learning, it's going to be helpful for you. And beyond that, you can most of the time just treat it as a black box. But it's also not very hard to do, and it's pretty fun. So I would recommend doing this. And it will like deepen your intuition a little bit for what's going on, and potentially help you avoid that one random bug that could have sucked up 2 days of your life if you hadn't understood this stuff. And so Andre Karpathy has an amazing sort of set of YouTube videos re-implementing GPT-2, an earlier version of GPT-3 and GPT-4, and the implementation is like less than 400 lines of code from scratch, including like all of kind of like what's happening under the hood. So this is like a pretty low effort kind of weekend project, or if you have a slow day at work or something like that, it's a fun thing to do. All right, I will pause there, see if there's any questions on kind of like fundamentals of machine learning. I know we went through this really quickly, but hopefully this gives you a little bit of intuition if you haven't seen this material before. Yeah.
Very similar.
Yeah, so the question is examples of validation versus testing. So if you recall, rather than training on all of our data, we instead split the data into 3 subsets. And the reason why we split it into subsets at all is because if we didn't have any data that the model didn't train on, it would be impossible to know whether the model was going to generalize or whether it just memorized that training data. But one question you might have is like, why 3 subsets? Like, why do we actually need 3 subsets? Why not just have 2 subsets? One for training and then one for validating. And the reason why we have 3 subsets is because oftentimes when you're training a model, you don't just like press train and then you're done. Like, you often need to try a lot of different things in order to see whether the model is, like in order to find the right model architecture or the right set of parameters or hyperparameters for your algorithm, or the right initial data set, or like all these other different factors that go into training a model. And so every time you train that model, you need to, in order to tell whether it works, you evaluate it on this held out data that it wasn't trained on. And so it turns out that if you do that enough times, and enough like isn't even that many, it can even be like a dozen or 100 times, then even though you aren't actually training on that held out data, by selecting the hyperparameters or the model architecture that works best on that held out data, you are sort of unintentionally overfitting to it, right? So like your human intuition about which model parameters are working best is selecting the one that works the best on the held out data that you're evaluating on a lot. And so the reason why we have a third held out data set called the test set is to sort of put a check on that process of overfitting. So even if you are like trying all the different things to make the model work as well as possible on the validation set, so that sort of first held out data set, you still need to check whether it's working on a third held out data set to avoid the problem of I just guessed too many times and I eventually got the answer. Yeah.
You mentioned that Hugging Face has
180K, different, could be more, of course. So if I have to use that in production, right, is it the right place? Should I be concerned?
Concerned about using Hugging Face models in production?
Right.
I would say I would be concerned about using any model that someone else built in production. Because you don't really know, like, the key thing is, even if you're using a pre-trained model, you still need to validate that it's going to work well for your task. And so we'll talk about, not in a ton of detail for Hugging Face models, but we'll talk about like kind of some high-level ways that you can try to test out whether the model that you're grabbing off the shelf works for your task or not. Maybe I'll take one more, and then I want to keep moving here.
Hi, my question is mostly about feasibility or like large language models where we're at the moment. I work for Walmart Search, and I know when our team looked at this, at this point it seems like it's not feasible with current pricing model. Like, for example, you know, we probably partner with Azure, and the pricing scheme is basically, it's too expensive if you hook it up to every user query. Where do you see, like, what's going to happen in this sense? Is it going to become cheaper, or where's the way to go?
Yeah, so the question's around like cost feasibility. And so for some applications, like modern large language models are just way too expensive for using them to make sense. Cost is coming down really rapidly. I think even last week, OpenAI introduced like I forget the number, but like a pretty significant cost decrease for GPT-4. Does anyone know what it was? 3x? Yeah, 3x cost decrease. And that's like, I think their second big cost decrease this year. So I think the cost of running these models is coming down like something that is much faster than Moore's Law. So still good to know about what the cutting edge systems can do, because what's cutting edge today is going to be, in 2 years, is going to be like pretty cheap to run. All right, so let's talk a little bit about large language model. So large language model is kind of a fuzzy term, and like a lot of researchers kind of hate the term. But when I say large language model, usually what I mean is like a transformer-based model that has at least 1 billion parameters. So like all of the matrices in that neural network together, there's more than 1 billion of them. And it's trained, like the task that it's trained on is to take a sentence, take a paragraph of text, and predict the next token, the next word or the next character that's coming in that sequence. So I want to talk a little bit about how modern large language models are trained, with a focus on the data that they're trained on, because the data that large language models are trained on is really important to understand in order to build intuitions for what these systems will do well and what they won't do well. So let's go all the way back in time to, you know, prehistoric era of GPT-2 back in 2019. So GPT-2, you know, was a 1.5 billion parameter model, and sorry, I'm having trouble with the slides here. Does that change if I do that? Okay, yeah, I guess it's just not showing up here correctly. Which was really, really large for the time, and now would be considered, you know, pretty tiny by large language model standards. So what data was GPT-2 trained on? The authors of the GPT-2 paper found that if you just like basically take all of the data from the internet, which you can find in this data set called Common Crawl, which is just like an open source data set that has a web crawler that basically pulls data from all websites. This data has massive data quality issues. So if you imagine just like random data from the internet, some of it is really useful and high quality, like thoughtful blogs, news articles, Wikipedia articles, but most of it is just pretty much garbage. It's like kind of random like HTML tags, advertising, stuff that you wouldn't really actually help a model understand the world better. And so they formed a subset of the Common Crawl data set called web text. And really the way that this was formed is they looked at Reddit data. And I think when people think about this, they think of like kind of all the comments and all of like the nasty stuff that happens on Reddit. But in reality, this was looking at the outbound links from Reddit and in particular the ones that people on Reddit had flagged as being higher quality by upvoting it on the Reddit system. And so this is the data that it was trained on. And so they were left with like around 8 million documents or around like 40 gigabytes or so of text. So this is GPT-2. GPT-3 was, I think, like one of the first sort of big breakthroughs in language models that started to make these things feel more general purpose. Like, I remember interacting with GPT-2 and it felt like the model was doing a reasonable job of guessing. It like felt impressive for a model, but it wasn't actually doing anything useful. GPT-3, for me at least, was the first time when it seemed like language models were actually going to be really useful very soon. And so GPT-3 wasn't really an advancement in any way in the underlying technology. Like it wasn't an algorithms advancement. It wasn't an advancement in the way that things were trained. It was just like GPT-2, but 100 times larger. So rather than 1.5 billion parameters, it had around 175 billion parameters. So a lot of engineering went into scaling it up like that, but not a lot of research or like changes in the fundamental technology. One of the reasons why GPT-3 felt like such a big advance is because it started to be really good at being able to kind of figure out new tasks quickly. And so this is like one of the kind of core experiments from the paper where they showed what happens, like how the model is able to generalize from a handful of examples to solve a new task. And so this task is, or this benchmark is in context learning. And so what that means is like, rather than training a model on lots of new data, instead what you can do is you can just pass a handful of examples to the model in the text that you input to it, in its prompt. And so one of the like amazing things about modern models like GPT-4 is if you give them a couple examples of what you want them to see, or even just a description of what you want them to see, they're able to figure out what you want and generalize that to new examples pretty well. GPT-3 was really the first time that we started to see this. So as the number of parameters went up to, from 1.3 to 13 to 175 billion, there was a superlinear increase in the model's ability to generalize well from a small handful of examples. So GPT-3 was trained on a much larger data set, which is one of the reasons why it was able to generalize better. And so this included like a lot of the data that was trained, that GPT-2 was trained on, but also a lot of other data from this messy common crawl data set. So a lot of the effort that went into building GPT-3 was really around scaling up the engineering side of the model architecture and figuring out how to just shove way more data into it. Like figuring out how to take all this noisy common crawl data, filter out the stuff that wasn't useful, focus only on the high quality examples and put the rest of the examples, and put those examples into the model's training set. So if you want to train large language models or even fine tune large language models, the lesson here is a lot of the stuff that's worth spending time on is filtering the data. So this model was trained on like 500 billion tokens. Unfortunately, GPT-3 data set and all the subsequent data sets for most of the like commercial language modeling companies are not, you can't get them. Like these companies, even if they're open sourcing the models, oftentimes they consider the data set their sort of proprietary advantage. So you can't just download the data that GPT-3 was trained on. The closest thing to an open source equivalent is from a company called Eleuther, and it's a data set called the Pile, which is about 825 gigabytes of sort of English language data with like lots of different sort of like high quality and diverse subsets. So it's not just one data modality, but it's data from all kinds of different places on the internet. So GPT-4 kind of started the era where not only did they not release the data set, but they also didn't really talk about what is in the data set, unfortunately. There isn't actually like a way to know even how the data set was constructed for the most modern models like GPT-4. But, where's the data? But we'll talk in a little bit about like some of the, at a high level, like some of the different types of data that the models are being trained on these days, because it'll give you intuition for where the capabilities of these models come from and where to go look if you're having trouble with the model working on a particular type of data. So one other point I want to make here is not only is the amount of data that these models are being trained on increasing rapidly, also the amount of compute being used to train these models is increasing exponentially. So if you go back to the original GPT or GPT-2 in 2018, 2019, these models were trained on somewhere between 10,000 and 1 million petaflops, roughly. These days, models are being trained on well over 1 billion petaflops. And training a state-of-the-art language model from scratch is getting to the point where it is completely infeasible from a cost perspective for almost anyone other than very, very well-funded startups, large companies, and government organizations. Like the rumors are that the next generation of models are going to cost something like $100 million to train. So another reason why training language models yourself is not really something that you need to be super concerned with at this point, but fine-tuning is still a helpful tool to have in the toolkit. So a concept that you'll come across in the machine learning world is called the bitter lesson, right? So like if you think about the history of GPT-2, GPT-3, GPT-4, I think what researchers wanted to happen subconsciously is they wanted to be like the genius breakthrough, the change in the algorithm that made something that was infeasible become feasible. And the bitter lesson is that, no matter how much effort you put into research and algorithms and clever ideas, almost always you're going to get beaten by someone who just figures out how to stack more layers and shove more data into the algorithm and spend more money to train it. So this is, I think one of the kind of age-old lessons in machine learning is that simple things work well. More data and more compute wins over more clever ideas. We're starting to see cracks in this a little bit, by the way, which is that the rumor is that the latest models from OpenAI are not meaningfully bigger than the last generation of models. And so the algorithmic advances are starting to matter again. And the reason why they're starting to matter is because OpenAI has essentially run out of data to train these models on. Like they don't have orders of magnitude more data than they did when they trained GPT-4. And so they're needing to rely more on algorithmic advances. When we tell the story so far of like how these models were trained, you get the impression that these models were trained on like basically the entire internet, which is true. But there's another part of the story, which is that there's other layers of data, layers of more specialized data that these models are trained on that are really important to the capabilities they have now. So if you just train a model on the internet, then what you get is a model that like kind of knows how to predict data on the internet, but it doesn't necessarily know how to solve tasks. So at the time that GPT-3 was created, the mindset that people had was like let's try to create a model that's general purpose in the sense that I can give it a handful of examples and it'll figure out how to generalize from those examples. But by the time that ChatGPT came around, the way that we interacted with these systems is really different. Like if you interact with ChatGPT, you're not providing it a bunch of examples of what you want it to do. You're just asking. You're just saying like, hey, can you write a document for me? Can you summarize this? Can you come up with ideas for names for my website? And so the mindset is now zero shot. Like the model should be able to do what you want it to do without you needing to show it, but instead just by asking. And so how did that ability come about in these models? How did the ability to follow instructions come about? And so the answer is fine-tuning, like a massive scale fine-tuning effort that was designed to help models be really good at not just predicting words on the internet, but actually following people's instructions. And so the way that this worked is OpenAI and subsequently most of the other developers of these large language models have curated much smaller data sets, but very, very high quality data sets of examples of instruction following. The way that this works is, if you have a bunch of examples of tasks that people want the model to do, which, if you're OpenAI and you release GPT-3 and you have thousands of people using it, you basically get for free. If you have that example, the data set of instructions, what you do is you basically pay people, pay contractors to solve the task in those instructions. And you maybe pay a lot of contractors to solve the same task so that you can quickly figure out which answer is, like, whether the contractors agree on what the answer should be or not. What that leaves you with is a data set that is much smaller than the whole internet, but still reasonably large, tens of thousands or hundreds of thousands of examples, where you have a really clean mapping between what the user wanted to do, like the instructions that they passed the model, and then what a human said an ideal answer would be. Then you take that data set and you fine tune your base model on that data set. And that produces, that gives the model the ability to take similar instructions that it sees in the future and solve the task that is contained in those instructions. So that's kind of like the first additional layer of training that happened to these models after training on the internet. And this is like a really critical part of what makes these models good, because it makes it so you can interact with them in more natural language. You can just ask for what you want and have the model produce it as an output. Then there's another like really important layer to how these models are trained, which you may have heard of. It's called reinforcement learning from human feedback. So the idea here is like, it's really hard and expensive and limited to ask contractors to describe exactly the ideal output that they want. Like if you imagine for more complicated tasks, if you asked a lot of people to write their ideal output, not only would it take them a long time and would it be expensive, but they also might all come up with like totally different things. And so the folks at OpenAI and other organizations came up with a cheaper way to gather feedback from people and use it to like further train the models. And that way is like, rather than asking people for what the ideal answer is, instead they have people rank different answers. So they'll give people two different possible answers, answer A and answer B, and they'll have humans just click on one or the other, like this answer's better or this answer's better. And so this allows them to collect preferences from people at a much larger scale and inject those preferences into the model. So when the trade-off that you make here by like gathering this simple sort of lower fidelity data is that the training process itself is much more complicated. But the advantage that you get is that you can collect human preferences on things that you might not be able to easily describe as in the form of a task that a human can solve. So the impact that this has had is that it's made the models significantly better at following instructions, and it's also made the models significantly better at avoiding some of the like kind of traps and problems with these models that people complained about when they first came out, like jailbreaking and going off the rails and saying crazy stuff. So one thing that you might ask is like, what is ChatGPT? Like, how does this fit into all of this? Like, how was ChatGPT different? Why was that such a breakthrough? The interesting thing is that like ChatGPT wasn't really a technological breakthrough at all. Again, coming back to the bitter lesson. OpenAI took the models that they were already using. They did a little bit more reinforcement learning from human feedback on data in the form of conversations, right? So the model is good at recognizing conversations and what kinds of conversations human preferred over the others. But really no kind of core change to the technology other than a change in the format of inputs that the models expected. So these models are now expecting data in the form of conversations. But it turned out that just reformatting the mode of interaction from needing to write an entire paragraph of text and have the model to respond and being able to interact with the model in a turn-based fashion as part of a chat made a huge difference in how usable it was for people. So I think like maybe one other point I'll make on GPT is, like you can think of GPT as sort of having a lineage. These models are not really trained from scratch anymore, or at least they're not trained from scratch very often. Instead, you take you can think of this as kind of a base model, which is the model that's trained on the internet. So this is the model that has like tried to compress as much of human knowledge as possible. And then it's fine-tuned over and over again on different subsets of data that give the model different capabilities. So those capabilities are instruction data sets, so data sets where humans solve the task for you. Reinforcement learning from human feedback data sets, so data sets where humans tell you their preferences. And then a third type of data sets, which is data sets of code. And these code data sets are also one of the keys to why these models are so capable, even for tasks other than coding. There's papers that have found that like training on code is one of the things that makes models better at forming like sort of logically cohesive sets of thoughts. One kind of implication for how these models are trained is that a lot of the recent work on fine-tuning, reinforcement learning from human feedback and instruction tuning is focused on like what you can think of as alignment, right? It's focused on helping the models avoid doing things that people don't want them to do. So, you know, again, if you remember back in the early days of ChatGPT when Bing first released their API and a lot of the negative press around like how journalists were able to get the Bing chat to, you know, express its really dark thoughts and you know, like go off the rails a little bit in a way that seems scary to people. That doesn't really happen anymore. And one of the reasons why is because of all of the reinforcement learning from human feedback that these companies have been doing on top of the models. But these additional forms of training, these alignment-oriented trainings that are aimed at helping avoid bad outputs from the models come at a cost. And one of those costs is that some people find that they're not as capable as they used to be at some tasks. So it's just worth knowing about. So there's been open source attempts to sort of reproduce some of these reinforcement learning from human feedback data sets. One thing that you can do is you can steal a lot of the training that these models have. So if you just ask ChatGPT to answer the question for you, that creates a data set that you can use to train other models. Questionably legal, but still pretty widely used in the research community. And there are open source models that have been released. Open Assistant was kind of like the first major effort that attempt to reproduce the ChatGPT's ability to kind of follow human instructions. So kind of rapid intro to transformers and LLMs. If you want to learn more about this, I recommend these resources to kind of like go a little bit deeper on some of the stuff that we covered here. Any questions? Yeah.
Oh, no. Yeah, really quick question. What exactly is a parameter? So you hear this phrase like, oh, it went from 1.5 billion parameters to 175 billion parameters. Does that mean that like they took a piece of data and effectively converted it into 175 billion like floating point numbers in a matrix for every single thing?
Yeah, so the way to think about parameters is like, you know, again, if the mental model for what neural networks are doing is it's just taking a vector of numbers and it's multiplying it by a matrix a bunch of times with some other kind of functions being applied to transform in between. A parameter is one of the parts of that algorithm that is learnable. So the weights of these matrices, when you start training the model, are all random. But throughout the training process, you know, you apply some basic calculus to adjust the numbers in each of those matrices a little bit at a time until those matrices are like well tuned to your task, like where multiplying by those matrices transforms the input to the output in the way that you want it to be changed. And so a parameter in a neural network is any of the numbers inside of that neural network that are learnable by that algorithm. And so kind of a good sort of rough mental model is it's like any of the numbers in any of those matrices. Sometimes, depending on the architecture, sometimes there's other things that are parameters. Sometimes some of those like weights in the matrices are not actually learned. They're hand coded in some way or another. But that's I think that's how I think about it.
Can you give an example or some intuition of how the transformer network differs from sort of a vanilla classic forward computer vision network that works very well on that type of problem? What's the big or what happens when you go from there to the transformer network? That is so fundamental.
The big innovation in the transformer, like if you think back to the name of the paper was "Attention is all you need." So why is it called "Attention is all you need"? There's an idea in deep learning that existed before the transformer, but was really like popularized by the transformer called attention. The way that attention works is like if you think about a typical kind of feed-forward neural network, there's many layers that are stacked on top of each other. Each one of those layers you can think of as a matrix multiplication. And so each of those layers, you know, if you think about this like stack of matrix multiplications happening on top of each other, the inputs to one matrix multiplication are the outputs from the previous matrix multiplication. And so in order to transform the output correctly, at each layer, so each of these matrices, all of the information that it needs to be contained in the output of the previous matrix. So if you're going from layer 1 to layer 2, or if you're going from your inputs to the first transformation, you can only look at the inputs. If you're going from the first transformation to the second transformation, you can only look at the output of the first transformation in a standard feed-forward neural network. And so it turns out that that's hard, right? Because you have to get it right. You can't accidentally throw away any of the information in any of the layers in order to get the final answer correct. So attention, the core idea of attention is that at any given layer of the network, at any given step in this transformation, you give that layer access to all of the previous information, and in particular to all the previous inputs. And the model learns to the model learns to incorporate all of that information in a different way depending on the layer. So the model is able to take any individual input and incorporate that information into its outputs. And that just, these models are equivalent in the sense that they're all capable of learning any function, but it turns out that attention and transformers are able to much more efficiently learn the functions that you're trying to get them to learn because of this mechanism called attention.
Hi, yeah, the instruction tuning, the skeptical part of me thinks, okay, they're no longer sharing what they're doing on the data side. They're hiring thousands of contractors to answer basically preformed questions, and then, and the answers maybe are picking the best answer. That sounds like a hack at best, or quite brittle, and not the same thing at all, really. And is that intuition wrong, that it's becoming more and more brittle if you do it that way, or is it the language model still doing some real work there?
Yeah. I guess my intuition is a little different, which is I think of it as what are you doing when you train a machine learning model? You are teaching it to follow a pattern. And so whatever data you put into the model during training, those are the patterns it learns to reproduce. And if you think about a model that is not trained very much, like a model that's pretty much random, there's a lot of entropy in the outputs that it'll produce. So you can write a sentence, and you put that sentence into the model, and it can produce pretty much anything. Produces something that's close to a random sequence of outputs. And so a lot of the purpose of training a model is to reduce that entropy, right? It's to make the model respond in a much more specific way to a given set of inputs. And so I think of these further processes of training on instruction data and training on preference data as constraining the types of outputs that the model will produce. And so reducing that output space. And that is very productive because it means that it's much easier to get the models to do what we want them to do, but it is also a constraint. And so it does remove some capability.
Okay, so my question is, suppose I'm training a domain data set on top of one of these LLMs. Is there any risk of overfitting that base LLM? And then the second follow-up question to that is there any guidance to the minimum amount of data set for that domain that I need to get an effective output?
Yeah, so anytime you fine-tune a model, there's always a risk of overfitting. And it's something you have to be very careful about in fine-tuning. And it's one of the reasons why fine-tuning is a lot more difficult than prompt engineering and techniques like that. In terms of how much data you need, it depends on what you're trying to do. These days you can get decent results even from hundreds of data points. But much more reliable would be to use thousands or tens of thousands of data points. Okay, I'm gonna keep moving because we're a little bit behind, and I wanna cover one more thing and then maybe we'll take a quick break, which is the anatomy of an LLM application. Okay, so we've talked a lot about how LLMs are kind of these like magic functions that can take text and follow instructions contained in that text and produce outputs to solve problems. But there's a lot of limitations to how LLMs work today. The first is that despite all this additional training, it can still be really difficult to get the model to do exactly what you want. And so, here's an example on the right where I was trying to get ChatGPT to correct the grammar of some inputs. And what's like the interesting example is at the bottom here when I typed like who is the top person in the world, and ChatGPT changed that not just to correct the grammar, but actually also to change the meaning of the sentence to who is the most influential person in the world, right? So this is not exactly, like if I was building a grammar correction bot, this is not exactly what I would want it to do. So it still can be hard to get models to know what's in your brain, to know exactly what task you want them to solve. And so that's why there's these kind of worlds of prompt engineering, task decomposition, and fine tuning that you need to know about if you want to get models to do tasks reliably. And so we'll talk more about that in a little bit. Second kind of big limitation of LLMs is that they don't know everything that you want them to know, right? They're trained on tons of data, but they're not trained up to the minute with the latest data. Up until recently, they were only trained until 2021. So they didn't know how to answer questions about current events, like about the way the world is today. Today, I think OpenAI updated them last week to be trained up to at some point this year. But they still don't know things that are not just contained in the general internet. Like if you have information that's specific to your company or specific like ways that you want the model to write or facts that you want to know, those are not contained in its training data. And so you need a way to give that data to the model so it can use it to solve the task you want to solve. And this is the process of augmenting models with tools and information retrieval, which we'll talk a lot about today as well. And then finally, it's like never been easier to get models to like kind of work, like to work most of the time or to work a handful of times, enough to produce a really cool demo. But it's still really, really hard to go from that prototype to a reliable production system. And so we'll talk about that as well in kind of discussion of LLM ops and test-driven development. So putting it all together, like I think there's kind of a pattern that's starting to emerge for how these LLM applications are built. And so I would divide this into like three pieces. The first is the part that the user sees, which the user puts in a request. That request is something like a question that they have for the system or a conversation that they're having, a document that they want to summarize, whatever input they need to provide in order for the algorithm to do its job. Then what's happening behind the scenes is they're interacting with an LLM application, and this LLM application has different components. The first is the instructions. And so the instructions in the middle here are like basically the prompt that you give the model or the sequence of prompts, the chain that you give the model that tells it the rules that it has for how to solve the task for the user. Those instructions interact with two other systems. The first is the model itself, which could be GPT-4 or another proprietary model, or it could be an open source model that you host yourself. And then the instructions also interact with external information. So they interact with like all the other data that you need in order to solve the task. Tools, retrieval systems, vector databases, and what OpenAI calls functions are the different ways that we'll cover for your LLM app to use external information. And then even further behind the scenes, if you're building an application like this, you have an improvement system. And the improvement system is what you are using to take the request that the user is making and the sequence of steps that the app is following to solve the task. Use that to better understand what your users, what problems they need you to solve, and make your application better at solving them. So this includes things like analytics, like looking at the logs of what your users are doing, testing and evaluation to validate whether the changes that you're making are improving things for users, and like a bucket of things that we will call LLM ops, which like is basically kind of the nuts and bolts of how to do these improvements, like managing prompts, fine-tuning, and hosting models. And so this is more or less what we're going to cover today. yeah, I think like maybe the last thing that I'll show today, or for right now, is just a really simple like batteries included example of how to do this. And I would think of this as like kind of a baseline for the stuff that we talk about later. This is the way that you would do this if you didn't want to think about it. And that's to just use the like brand new OpenAI Assistance API. So the way that this works, and can you still see this if I flip to the other thing? See code? Okay, cool. So this is like a chatbot that you can use to interact with the like all of the information from the previous FSDL course, like the pre-LLM FSDL course. And so we're gonna cover later today like a more in-depth version of how you could build this yourself. But just to give you a preview of like what this might look like to build in the future without understanding any of what's going on under the hood, this is how you would do this in the like new OpenAI API. And so really this is like consists of a couple steps. The first is that we have some data. And this data is basically just a pointer to the lectures from our 2022 course. And so we have, you know, the base URL for where the markdown for these lecture notes are stored, and then we have kind of a list of each of the lectures. So the first thing that we need to do is we need to like give OpenAI access to this data so it can use the data to answer questions. And the way that we're gonna do that is we are going to just call this function called upload data to OpenAI. And again, there's like, this is really, really simple. There's nothing here that is LLM specific. OpenAI is taking care of all the technical details about what happens to this data and how it's used by the model in order to answer questions. So what we're doing here is we're just downloading each of these documents, each of these lectures. We are rewriting them locally, which is just to have a local copy and to change the file name. And then we're opening each of these documents and we're calling the OpenAI client to create a file. So OpenAI now, after we run the script, has a file associated with, in its system, associated with each of these lecture documents. And so it has access to them in the Assistance API. So now that OpenAI has access to each of these documents, the only other thing that we need to do is we need to tell it how the assistant can use those documents to answer user questions. So we define an assistant. And this assistant like really couldn't be simpler. It's like 2 lines of code. So we give it a name, in this case it's Ask FSDL, and then we give it a set of instructions. These are the instructions for how it does its job. And so here we're just doing a really simple set of instructions. You're a teaching assistant for full stack deep learning, and your job is to answer questions for students. Put another line in the prompt here, which is basically trying to encourage OpenAI to always find the information in the lectures. One kind of common problem with these LLM applications is what people commonly refer to as hallucination. Hallucination, I think, is like pretty loosely defined right now. Like people say hallucination to mean basically any kind of failure that the model makes. The way I define hallucination, like a more technical definition for hallucination is when the model is supposed to respond based on information that it retrieved from a corpus of knowledge, but it instead just tries to respond to like make up an answer from the internet data that it was trained on. And so in order to avoid that, we add this other line which says, always try to find the information in the attached files using the retrieval tool. And so if you can't find anything, then don't attempt to answer the question. And so really the only other step here is we need to ask OpenAI to create an assistant for us. This assistant uses their new GPT-4 preview model, and it has access to all the files that we defined in the previous step, as well as, and it's able to access those files using what OpenAI calls a retrieval tool. So a retrieval tool is like all the details abstracted away of what's going on under the hood of basically everything else that we're going to talk about today. So this is the batteries included version of like, I don't want to understand the details, I just want OpenAI to handle it for me. Yeah, was there a question there?
Just one question concerning your usage. So you're instructing the model to use the retrieval tool, but it's super implicitly because nowhere is defined how you should call retrieval tools so that the model knows you should use the retrieval tools.
Yeah.
This is kind of implicit, right?
Yeah, and this is actually like, I've been having trouble with this in the assistance API. I think they maybe need a more explicit way to do it. I'll show you in just a second like how this fails sometimes. But yeah, I think like in OpenAI usually for their function calls, they give you a way to describe the function, which helps the model understand when it's supposed to use that function. The retrieval tool doesn't really seem to have the same level of control about when it's used or not used. So yeah, it's one, like, and I think we'll see in just a second that this was released by OpenAI last week, and it's, in my opinion, like nowhere near ready to actually use in production. And that's one of the reasons. But hopefully this gives you a sense of like, maybe next year when we teach this class, we won't need to cover any of the details of retrieving data or prompt engineering at all. It'll just all be taken care of by the higher level libraries that we use. So the last piece of this is just, like how we manage the chat itself. And so what's happening here is we just have like, I'm just gonna take input from the user, in this case just in the terminal. The example that we'll show later will actually be a Discord bot that you can interact with, but for now it's just a question from the terminal. And then we create what's called in like OpenAI world a thread. That thread is like a sequence of messages that is consumed by the model to produce the output. And so we create a single thread, a thread that consists of a single message from the user containing this question that I'm going to type in the terminal. Then we create what's called a run. And so the run is like how you take this thread, this sequence of messages, and attach it to a model, attach it to an assistant. So when we run a thread, what we're doing is we're passing that thread to the assistant that we just created, and that assistant is processing the thread and using that to create an output. So next thing that we'll do is we basically wait for this thread to finish. So I'm just polling every tenth of a second until this thread is until this run is in a finished state, so that I know that the model has finished producing its output, and I can retrieve that output and see what the model said in response. And then the last thing that we do here is we just pull out this. We just list all the messages in this thread. We pull the most recent one, and we print that out to the user. And then this is like some additional details about how we just make sure that the model tells us which document it's using to answer the question. So any questions on like this kind of OpenAI assistance way of creating a chatbot? Yeah.
I'm just curious if you can comment on the state of LLM apps after OpenAI, Dev Day, just because I think a lot of work, over the last couple months have been relatively simple, like apps where a lot of the work was put into maintaining your vector database, like how exactly you're, chunking your documents, like all of those things that seem to have been solved at least with GPTs, or at least like in a much easier out of the box state. And I think like the more complex LLM apps, maybe like a Copilot from Microsoft, there's like a huge barrier between where the community has been building and getting to that state. So I'm just curious, like if you have any reactions.
Yeah, I think kind of like just a general thing in computing is like people start with really low level stuff and they build abstractions on top of the low level stuff to make it easier and easier to solve the problems that people were solving over and over again with the low level things. And so I think in general, like the idea of the assistance API makes a lot of sense, and I do think for a lot of applications people build, you're not going to need to manage your own vector database or understand the details of chunking or any of those things. So I think like this or something like this is how most of these applications will get built in the future. Still important to understand how it works under the hood for two reasons. The first is because, I guess like spoiler alert, this doesn't work. In my opinion, this is a premature release by OpenAI. I think they pushed a little bit too hard to get it out for Dev Day. And it doesn't actually, like this chatbot is terrible. It's not going to actually answer the questions that we wanted to answer anywhere near as well as the one that we're going to build in a more custom way. And so, if you're trying to build today, I think you should still use the lower level stuff. Not to say that this won't get good eventually, which I think it will. And then the second is because, as you start to do more and more advanced things, it becomes important to be able to like look into the black box and customize the way that things work under the hood. There's a ton of degrees of freedom that you have about each of the steps in this infrastructure stack, and tuning any one of them can like produce meaningfully better results. So Yeah, I think eventually we're going to be using higher level libraries like this, but it's not ready for prime time yet. So if we actually run this, let's ask a question. So I'm going to ask the first question I think it should be able to answer, which is, what does the first lecture cover? So again, this is an earlier version of the course. One thing that you'll notice when I run this is that this is really slow, and it doesn't stream. Oh, that one was actually reasonably fast. So it's able to like find this source, and it tells me that it's the first lecture is course vision and when to use ML, and it covers like an introduction to planning, developing, and shipping ML-powered products, which is like a pretty good summary. A couple things that you'll notice here. One is that like this wasn't particularly fast. It doesn't feel nearly as fast as using ChatGPT. And also it didn't stream the outputs. Like if you use ChatGPT, you're used to things coming back one token at a time, one letter at a time, which makes the experience a lot better because it feels like you're getting an answer a lot faster. These are limitations of the system currently. It's slow and it doesn't stream. So, one of the more technical reasons this is not ready for prime time. Now let's, I'll show you like a bigger limitation here. So let's run the chat again and let's ask a more complicated question like, let's see. I guess, what is fine tuning? So yeah, again, very slow. And so it says, it seems that I'm encountering technical difficulties accessing the specific details about fine-tuning in the full stack deep learning course materials. Which, we know it's not experiencing technical difficulties because in the previous question, it was able to find the first lecture. So it's, I think it's like, for some reason, OpenAI has not really figured out how to chunk up the information the right way to put this in the context. The bigger problem though is that it's like, if I was building the system myself, there's all kinds of things that would cause this, and I would have a way to debug what was going on. I'd be able to look at like, hey, is it not retrieving the right documents for me? Is like the content of those documents misformatted somehow? Is the prompt not being constructed correctly? All black box in the OpenAI system. And so it's really, really difficult to know where to go from here in order to fix this. So again, I think like OpenAI assistance is not really ready for prime time, but I wanted to show you because this is like, this is like 10x less code than what we'll talk about later this afternoon. And this is the direction things might be going. So like you can think of the rest of the day as basically us rebuilding this OpenAI assistance version of the chatbot, but in a way that actually works. So I will, I'll take one more question and then I'll stop there and we should take a break until 11. Yeah.
So I built a chat bot using embeddings RAG approach. So it did really well. So I gave some documents, I got really good response. But when I ask a random question, which is not irrelevant to the documents, it's still trying to answer it. For example, when I ask US President, it's answering the right question, but I don't want it to answer because I want only look into my documents, the cons. So how can we do that?
Yeah, so this is a really common problem, right? Like I think so like if you think about the process that people use to train these models, the process really does two things, or you can think of it as doing two things. Like one is it's teaching the models how to understand natural language and how to follow instructions. So it's teaching models like how to reason and how to interact with people. But then the second thing that it's doing is that the model, it's not just learning the underlying patterns of how language and communication work, it's also learning the specific details about all the information that it was trained on. And so if you just interact with a model without it providing any information, it will answer for you based on the information contained in the weights, which is derived from the information that's contained on all of the internet. So sometimes that's desirable, like if you want to just have a model that's able to answer general knowledge questions about the world. But for most applications that, I would argue most applications that most businesses are building today, it's undesirable. Because you want the model to answer based on specific information that is relevant to the task that you're trying to solve. And so a lot of times what happens is that the model, it's like really hard to get the model not to just answer based on its general knowledge. It really wants to just reproduce what's on the internet to answer the question for you. even if it doesn't actually have that information in the data that was retrieved. So I think the best way that you can do that now is by adding something to the instructions to try to, convince the model not to answer the question if it doesn't have information available. So that was this line in the prompt here. Like, you should always try to find information in the attached files by using the retrieval tool. If you can't find any relevant information, don't answer the question. But you saw in this example, it didn't find relevant information because of what it imagined was technical difficulties, but it answered the question anyway. And it at least acknowledged that it didn't find this information in the retrieved materials, but it still kind of did this thing that we might not want it to do. And so it's very difficult to get models to follow instructions that run contradictory to the data that it was trained on. And that's, I think, like one big limitation of these systems today.